Good day. Now we are going to illustrate the use of the auxiliary equation to evaluate the solution to our second order differential equation. For instance, we can take one example among those examples I listed. So let's say we are going to solve this differential equation. Based on the auxiliary equation, the corresponding auxiliary equation is r square, which will be replacing the y double prime, plus 5r. The r is trying to replace our first derivative, then plus 6 equals to 0. So this is the corresponding auxiliary equation for our first example. So anytime we have the auxiliary equation, the solution to the differential equation reside on just evaluating the roots of this auxiliary equation. So we can do it by factorization or by using a formula, but I want us to solve this analytically, and I want you to practice this analytical way of solving the roots of the equation, our auxiliary equation, so that we don't have to waste time thinking of about the factors. So the method is just completing square. So we first of all write down our bracket. Out of this 2r, we put r. The sign here, our sign here, we put it here. This sign, whatever is here is what we will put here. Then we'll now look at the coefficient of r. The coefficient of r here is 5, so we are going to put 5 over 2, right? We put 5 over 2. Now we square. We always subtract here, whether this place is plus or this place is plus, whatever is the sign here, we don't care. The procedure is to put minus here always. Then when we put minus here, we will now square this and put it there. So 5 square is 25. 2 square is 4. This is what we will write here, right? Then we will now transfer this sign here plus, and we put our 6 here and equate it to 0. This is what we will do. So we subtract 25 over 4 plus our 6 equals to 0. So this is how we can use the completing square. So what remains is just simplifying this. So we can now take the absolute term to the right hand side, the entire term here to the right hand side. So we have 1 over square equals to, when we transfer minus 25 over 4 to the right hand side, it becomes positive. And when we transfer our plus 6, it becomes negative here because of this equality, right? So we now solve this. So we can say 6 over 1, or LCM 4. So here we have 25 minus 24. 1 into 4 times 6, 24. So that is what we have here. So if we simplify, the numerator is 25 minus 25 minus 24, which is 1 over 4. So here is just 1 over 4. So the right hand side is 1 over 4. So what we have here is r plus 5 over 2 square equals to 1 over 4. So we take square root of both sides. This leads us to r equals to minus 5 over 2 plus minus 1 over 2. The plus minus 1 over 2 is the square root of 1 over 4. That is this. And since here is plus, when we take it to the right hand side, it becomes negative. So these are our roots. Minus 5 over 2 plus 1 over 2 is one root, and the minus 5 over 2 minus 1 over 2 is the second root. So we have our two roots here. So our two roots will now be root 1 equals to minus 5 over 2 plus 1 over 2, which is leading to minus 4 over 2, which is minus 2. Well, R2 is going to be minus 5 over 2 minus 1 over 2, which is minus 6 over 2 minus 3. So these are our two roots. So immediately we arrive at these two roots, we have finished. We can now construct the solution to our differential equation. Now the solution is now simply y equals to a constant exponential r1t plus another constant exponential r2t. Our r1 is minus 2, our r2 is minus 3. Therefore, our solution is now y equals to a exponential minus 2t plus b exponential minus 3t. So this is our final solution of this number 1. Right? So I want us to apply again, try to use the same procedure and solve all these 12 questions. Solving them will help you to master the method. So let me take another example. Here. I want us to solve another example, maybe in another category. The solution to our first equation, you can see all the roots are negative. And if we have all the roots are negative, we have, the amplitude B and A are going to be dying with time. So therefore, we have a overdamped case. So this is overdamped case. That is, this is dampened. This is also damping because the exponential is negative. No problem. I'm going to explain some of these things. So let's say another one here, which is no. Let's take the other one in this case here. Let's take this one. Okay. So now apply the completing square techniques. Based on our equation y double prime minus 4y prime plus 3y equals 0, our corresponding auxiliary equation is going to be r squared minus 4r plus 3 equals to 0. So if we apply the same technique, we will now just say r minus, because this is minus, so r minus 4 over 2 square minus 16 over 4 plus 3 equals to 0. So if you simplify this, you are going to get r minus 2 square, right, minus 4 plus 3 equals to 0. Taking this term to the right hand side will give you r minus 2 square equals to 1, positive 1, because minus 4 plus 3 is minus 1. Minus 1 to the right hand side become 1. Therefore, your r will now be 2 plus minus square root of 1, which is 1. So this will give you your roots. So you can easily see that root 1 is going to be 2 plus 1, and root 2 is going to be 2 minus 1. So our 2 roots is now going to be 3, and our root 2 is going to be 1. So our roots are 3 and 1. So therefore, the solution to this simply is y equals to a exponential r1t plus b exponential r2t, which will now simply be y equals to a exponential 3t plus b exponential t. So this is the solution to this. In this case, all the exponents, the power are positive. So in that case, we have an unstable case. Okay, unstable case, and because that is what we have solved now. So I will advise you to solve all the remaining questions and practice solving them using the completing square. So far, if we have this kind of equations, we will make use of complete and square to find out the roots. However, it's good I illustrate if our roots are complex numbers, what do we have? So let's see a complex case. A typical complex case is somewhere here where the roots are complex case come here. Yeah, the roots are negative. So let's see a complex number. So let's take this one now. If we write the corresponding auxiliary equation for this equation is r squared plus 4 equals to 0. So r squared equals minus 4. If we take square root, we will have r equals plus minus square root of 2 minus 4, which is 2i, where I is the square root of minus 1. So this is a complex number. So anytime we have complex number, anyway, our roots are now what? R1 is going to be 2i and R2 is going to be minus 2i. So if we substitute this directly into our normal expression of the solution, R1t plus b exponential R2t, we will end up with y being a exponential 2it plus b exponential minus 2it. Right, so that is our solution. This is our solution to this. However, anytime we have exponential I theta, we use Euler's relation, Euler's formula, which says that exponential I theta is equivalent to cos theta plus I sin theta. Right? So anytime we have we have our roots to contain complex number, we can go ahead and substitute cos Euler's formula there. So let me illustrate how we can solve resolve to the cosine and cosine. Right? So I think it's good we substitute that result. So let me say that since ei theta equals cos theta plus I sin theta, so my y here becomes y equals to a exponent a cos 2 theta cos t plus I sin 2t plus b inside here cos 2t minus I sin 2t. Right, so opening the bracket will give me, I have a plus b cos 2t. When I take this and this term, then I will now take this term and this with I and this term. So I will now say plus a I minus b I sin 2t, right? Then plus I've now compiled them. Yes, I have my 4 terms. If I open this is a cos 2t plus ai sin 2t plus b cos 2t minus bi sin 2t. Yes, so the term was I, this one and this one, so they are accounted for here, and the term without I, this one and this one, and they are accounted for here. So I can now, since a is constant, b is constant, I can call this p. A, I, b, I are constant, I can call this q. So my simplified result may be just p cos 2t plus q sin 2t. So straight, anytime I have complex number, I can just go ahead and put cos 2 and cos and sin to replace my complex number. I mean to replace my a exponential at, whatever it is. Instead of that, I will write sine and cosine. right? So I think that is all I want you to remember with the equation. Now let us discuss the nature of the solution. Why I have up to 7 different categories is because of the nature of the roots. So we come back. We have 3 major issues here. So if our roots are all positive, so here this is the nature of roots. If our roots are all negative, they are negative. Any negative root indicates decay. For instance, I have exponential minus 60. So this is trying to show me decay. So if I will plot this graph, I will end up having something like this. The curve of this is going to come something like this. So this is a decay, right? So, and when we have, anytime we have decay, we can say the system is stable, because anything that causes the growth here is going to be dying with time, so it's going to go out of the system. So we can say the system is stable. Another thing is that if our exponential is positive, exponential is positive, we have exponential 60. So if I will plot this, I'm going to get something like this, and this is gross. So this is gross. Okay, this is gross. So anytime we have positive exponent here, we are going to have grow, and if the same thing that create this is very small, it will grow like this exponentially. So this growth can bring instability sometimes, so unstable. So anytime we have positive roots, the positive root is indicating the system is going to be unstable. So negative value here is decay, and the other term of the decay is damping. So it's damping. That means it's killing the vibration, or killing the system amplitude, right? So based on that, we have these different types of cases we can encounter here. Based on the nature of the roots we have. So that's why I have all these 7 different categories. So here I'm saying if you have real and distinct, both negative, you have an overdamp system. The system is going to be overdamp, meaning that if it is vibration, the vibration will die quickly. Just like some doors, which I want to some doors with some killing vibration material attached to them. And when we have repeated roots here, anytime we have repeated root and the roots are negative, we can say they are critically damp. Okay, critically damp. These are just typical critically damp system. And if our roots are real and distinct, and both of them are positive, we have an explosive unstable case, which I am going to illustrate to you what is that an explosive unstable case. And anytime we have our roots, one is positive, one is negative, we have saddle unstable because of the positive unstable. Because of the negative is somehow is trying to stabilize, but we have a saddle case, right? And anytime we have our roots, all of them are complex, then we have pure oscillation there, pure oscillation. If we have complex and they are real, we have we have zero real part, there is no damping. So we have a complete pure oscillatory motion. And anytime we have the complex root and we have negative real term, we have a stable oscillatory system. And when we have positive tau, we have unstable oscillatory system. All of this system are illustrated here. These are the illustration of the different cases we have discussed. Yeah, so all of them positive values, we have damping, stable and damping. They are all less than 0. So we have negative roots. All the roots are negative, so it's over damp. This door, when you open this door and release it, it's not going to bang. It's not going to come here. When you release it, it's going to come back, but it is coming back. It's going to come back to its original position, but it's going to come back slowly. Due to what? Due to the damping. And who is creating the damping? This arrangement is what is creating the damping. The door is not going to come back quickly to hit this wall. No, it's going to come down slowly because you have attached a damping term to it. This damping term is governed by the equation similar to our equation number 1. And these are the cases where we have explosive unstable, meaning that this pencil, when you try to when you release it here, the restoring force, that the weight of the object will just cause it to fall down. It's going to fall down, so it's not going to be stable. It's not going to stay here, and therefore it's not stable. And even if you blow it with wind, it will just fall. So a small force can create more displacement on the pencil, and that's the kind of thing you will have here, small displacement. Well, here you can see that when you release it, it's going to die with time. Similarly, we can have the two cases where we have the saddle. One is positive and the other root is negative. The positive is indicating growth, this line, and the negative is indicating decay. So if you have your pendulum here, when you release it here, it's not stable, so it has to come down here, right? It has to come down there. But when it is trying to move to this side, there will be G, which will be forcing it to come down, and this side is going to be negative, right? Going here negative is going to kill the going, and coming here is positive. So this is a kind of a saddle case. One aspect, the thing is not stable, and another aspect, when it is living here, trying to grow here, that movement here is going to be with damping, right? Here with growth coming, and when it reaches here, it is trying to move here, damping. So positive exponent here, negative exponent here. That means this one handle this, while this one handle this side when it is going in this direction. Right, so this another, when we have pure oscillation, is something like this, where we have the root is purely sine or cosine. So this thing can remain to vibrate, or sometimes if you plot it, it's going to give you something like this. And we can have a vibrational motion, but with damping. And the damping is light. If the damping is light, here is where the damping is. So if it is small negative value, so it's going to be dying with time. It's going to be dying. And the last one is where we have the oscillation, but the oscillation grow here. So this is going to be highly unstable case. So these are the cases I want us to illustrate, to have some illustration where we can apply them positively. So the next thing is to look at the inhomogeneous cases.